Okay, morning class. Today we will continue on the topics of Laplace transformations. Okay, but the approach is slightly different from what we have discussed previously, in the sense that we will transform the circuits into Laplace domain directly without having to even write down the differential equation. Let us review what we have done so far. Okay, you have learned how to write down the circuit's law. For resistors, you use Ohm's law. For energy storage element, the relationship between voltage and currents are no longer just proportional. They are related by some differentiation. For example, I is equal to C dVdt for capacitors, V is equal to L dIdt for inductor. As such, if you put it into your circuit's law, you will get something like a differential equation, right? Such as for RC source free, you get these differential equations. And for first order system, you can easily solve it by integrating by parts, right? Separations of the variables, actually. Okay, but however, for higher order systems, for example, second order systems, some of you will be wondering, how do we get this three types of solution? Actually, it's from Laplace domain. So Laplace transformation is a more powerful way to solve problems involving differential equation, right? Such as your circuits involving energy storage element. And the idea that we have learned last week is that you first write down the circuit's law in the form of differential equations, and then you transform it into Laplace domain by using differentiation property, because dVdt in time domain is equal to SVS minus the initial condition in Laplace domain, right? Take note that the differentiation disappears, is replaced by SVS. So once you see a signal Vs multiplied by S, implies some kind of differentiation in the time domain. Okay, and for the other terms in the differential equation, you make use of the linearity property, right? 1 over RC is a constant multiplied by Vs, while Vs is the Laplace transformations of Vt. Usually you use a capital letter to differentiate from the time domain signals, and then of course the argument inside will be S, right? Laplace variable. And after that we get algebraic equation because there's no more differentiations. Therefore you can just solve this equation in terms of S. Okay, the only additional step is that in the end you need to take inverse Laplace transformation to get back your signals, right, in the time domain. What we want is the solution in the time domain, but we can't solve it in the time domain easily. So therefore someone create a virtual domain, mathematical domain called Laplace domain, S domain, where we can solve the equations easily through algebraic manipulations, and then after that we take inverse Laplace transformation. Now, while taking inverse Laplace transformations, if you cannot find the solutions in the table, then you should use partial fractions to expand it as a linear combination of the terms that can be found in the table, right? Then you use linearity property to take the inverse Laplace transformation. And as I said, right, you need not remember all these properties or tables because you will make use of the table provided. Even in the examination, Okay, you'll be provided with these properties as well as the table. Now for this circuit theory, you only use, right, n equal to 1 is here, first order, n equal to 2. You have to use these equations, that means just substitute 2 here. D square f dt square is equal to S2 Fs, right, minus the initial conditions related to the initial signals as well as the differentiation, right? This df dt, differentiations of the signals at t equal to 0. S equal to 0 is 1. Right? That means that you use S square Fs minus Sf0 minus, this is 1, initial conditions of df dt, right? Okay, but today we will learn new methods, right, without having to even write down this differential equation anymore. Okay, the idea is that we look at the circuit elements directly and then get the model in Laplace domain similar to Ohm's law so that we can solve it, right, using the methods that we have learned in week 1 and week 2, right? We shall see that. And this is a Laplace transformation tables. Left to right is from time domain to Laplace domain. Right to left is from Laplace domain back into time domain. Find your solutions over here, then express as the linear combinations of them. Okay, the key idea is that your solutions should be expressed as linear combinations of what you can find on the right hand side. Then you can use linearity property to transform it back into time domain. This is just the table that you will see, right, exactly in your exam paper, right? So need not remember that, but you can use these tables, right, to get familiar, right, with it. Okay, today, as I said, we will learn something which is different from last week without having even to write down the differential equation. The key idea is to look at each circuit elements, right? We have only a few components, resistors, capacitors, and inductors. Okay, for resistors, there's no change actually because V is equal to IR. Therefore, when you take Laplace transformation, Vs is equal to R Is. Is is the Laplace transformation of It. Vs is the Laplace transformation of Vt. This means that V over I is R. Therefore, in Laplace domain, right, resistors remain, right, because there's a linear relationship between voltage and current. Okay, but for inductors and capacitors, right, there will be a difference because V is equal to L di dt. Right, as I said, you need to remember this by heart. Okay, remember this by heart because it will tell you a lot of information regarding the properties of the inductors, and you can also transform it into Laplace domain. Yeah, even if you forgot the formula, just refer to this table. Right, it will tell you that dV dt is SVS minus V0, correct? Then you know that I can naturally transform it into Laplace domain by using this time differentiation property. In the sense that di dt, right, will be SIS minus, right, the initial current, minus the initial current. Now let's start with zero initial condition, meaning that there's no initial storage, right? No initial storage. These are storage elements. You need to first supply with energy, then you will be able to discharge it back to the circuits, even if there's no source, right? There's a store energy. But just like a spring, if you pull the spring to a certain equivalent point, actually you're providing some potential energy through your hand, the force, right? Once you release it, actually it's releasing the store energy. Okay, in this case, let us suppose that there's no store energy initially. Okay, and in this case, right, there's got to be some supply somewhere in order to result in the current. So if you put a supply somewhere and there's a current flow through it, okay, then the relationship between voltage and current in Laplace domain is actually something similar to Ohm's law because Vs is equal to SLIS without initial conditions, right? V over I is SL. Now you should remember this, right, by heart. If you forgot, then refer to the table, spend one step to remind yourself, right? But I suggest that you just remember it because this will be faster, right? SL is... Sorry? What? I'm having a class now. Yeah, so you're in this class? Yeah, I'm having a class now, so you want to attend, you can attend. If I have time later on, right, then I can handle your question. Not now. Yeah. Okay, so I'm sorry, there's a interruption. Now, I was saying that in Laplace domain, the relationship between voltage and current becomes something similar to Ohm's law, right? In the case of resistor, V over I is RL. In the case of inductor, V over I is equal to SL, okay, which means that if you put your circuits into Laplace domains by transforming inductor into SL Laplace domain, okay, whatever that you have learned in week 1 and week 2 can be applied similarly, right? So this is the objective of this week tutorial. Similarly, I is equal to C dVdt. dVdt is equal to S Vs minus the initial voltage, zero initial conditions, meaning that no voltage initially. For example, your handphone fully discharged, 0%, right? And then you start charging out from 0%, and this is how your circuits will behave. V over I will be equal to 1 over SC. Okay, again, remember this by heart. So inductor SL, capacitor 1 over SC. Okay, by transforming capacitors into these circuit models, 1 over SC in Laplace domain, you can similarly use what you have learned in week 1 and week 2 by treating it similar to a resistor network. Right? So to summarize, for resistors, V is equal to IR, inductor, V is equal to I, SL, capacitor, V is equal to I, 1 over SC, or I divided by SC. Okay, in other words, V over I is RL for resistors, V over I is SL for inductor, V over I is 1 over SC for capacitor. Now, these concepts, right, we call impedance, right? It's just a name to include this energy storage element in the Laplace domain. Okay, in the sense that in Laplace domain, VOI appear as a kind of linear relationship similar to Ohm's law. So we call this, right, impedance. When you see the word impedance, it means that you include your energy storage elements, okay, in addition to the resistors. Now remember that for resistors, you have something called conductance, 1 over RL. So similarly for inductor, you have 1 over SL. Okay, for capacitor, you have 1 over SC, okay, which is actually SC. And this we call admittance, right? It's just a name to include this conductance of resistance, right, as well as inductors, inverse of the impedance. It is called admittance, in other words. Okay, you may want to use this formula to review what you have learned in time domain, right? Because it is now easier, because by transforming the circuits into Laplace domain, right, we can make use of the similar property as we have learned in resistor network. Remember, for resistors, if they are in series, you add up the resistance. In Laplace domains, if you have two components in series, you add up the impedance, right? Add up the impedance. For example, if I have a few inductors in series, right, with different inductance, each of them is SL. So you have SL1, SL2 to SLM. When you add them out, you can take out the common factor S, and then this will be your equivalent inductance, okay, which is exactly the same as what we have learned in time domain, right? If they are in series, you add up the inductance. The capacitor is the reverse, because now you can see that it's 1 over SC. Therefore, if you add up the impedance, 1 over SC, 1 over SC2, for example, then you take out the common factor 1 over S, okay, this whole thing is 1 over CEQ, okay, which is the same as the time domain, right, formula. So even if you forgot this, right, you can actually just work out one example, very simple one, to remind yourself. Okay, but of course, you have to remember this by heart. SL, 1 over SC. Then you try adding them, you will get the so-called the formula that you want. So in Laplace domains, right, everything can be reviewed for the time domain in a similar way. Now, even for the series RLC, parallel RLC, actually you can use it to derive the characteristic equation. I'll show it to you later on. But if you have series RLC, this is what you'll do. You have a resistor in series with an inductor, in series with a capacitor, right? So you should add them this way. The difference is that, of course, you can't simplify further by grouping them as in resistor or inductors, capacitors, right? You can add them because they have the common factors, S, 1 over S, and in case of resistor, it's scalar. Okay, here you can't add them, you leave them separately, right? Leave them separately, so this is a difference. Okay, as for parallel combinations, remember for parallel combinations of resistors, you add up the conductance. So similarly, for parallel combinations of capacitors and inductors, we add up the admittance, okay, in the sense that if we have parallel combinations of any components, we just add up the inverse of the impedance, which is called admittance, right? 1 over Z is called admittance. For example, 1 over SL, right? If you add them up, then you get the equivalent inductors as 1 over L1 plus 1 over L2, right? For example, for two parallel combination. Okay, as for capacitor, right? Because the 1 over SC is SC. This means that this is just adding up SC, right? For C1, C2. So the equivalent capacitance is just the summations of your capacitance. Okay, parallel RLC that we have learned, right, in the time domain analysis is 1 over R plus 1 over SL plus SC. So this is basically parallel combinations in the sense that you add up the admittance. Series combination, add up the impedance. Okay, therefore, you can see that everything that you have learned in week 1 and week 2 can now be similarly applied. Right? So in this tutorial, we'll see that we will link it up back to week 1 and week 2, and then use it to solve the circuit problem. This is the reason I keep stressing that week 1 and week 2 are very, very important, because you got a chance to review it over and over again, right, over the weeks. But if you do not start, of course, right, you will not enhance your understanding over the weeks. Okay, let us now start solving the first problem of this tutorial. Now take note that it is stated that the capacitor is initially uncharged, meaning what? Zero initial condition, right? We're going to find what happened after that. Okay, starting from 0, that means that you start from 0 volts, initially uncharged, find the voltage. After that, also take note that the source, right, is not DC or AC, is something with a delta sign. Right, this is actually an impulse signal. You can check your table for the notations. There's a delta there right from the top. Right, therefore, we need to transform this into Laplace domain as well. Okay, let's start from this energy storage element. For capacitor, right, I is equal to C dV dt. Again, we know that in Laplace domain is 1 over SC. C is equal to 1, therefore is 1 over S. So your energy storage element capacitor become 1 over S in Laplace domain. The other signals also put it similarly. IT become capital IS. 4IT is 4IS. V0T is V0S. Right? So we just put all the signals. Okay, the other one is this source. 15 delta T. Check your Laplace transformation table. Delta T is equal to 1. Right? So therefore, when you see a constant in Laplace domain, it's not a constant in time domain. In time domain, in fact, it looks like this. Right? It's an impulse. At t equal to 0, you just pulse it, and then after that, it drops back to 0. Then, in Laplace domain, it's actually constant. Right? Now, a constant in time domain, for example, a unit step, right? 1. 1 is constant for t. Unit step basically means that it's equal to 1 for t greater than 0. Now, in Laplace domain, it's not constant, it's 1 over S. Right? So be careful of that. Constant in Laplace domain is an impulse. Right? 1 over S in Laplace domain is actually equal to a constant, right? Unit step. So for this one is 15 is not so-called DC, right? It's an impulse because we have put it into S domain. Now look at this circuit. Imagine that you have a resistor here. What will you do? Right? Do it similarly. Right? So this is what the idea. Once you put things into S domain circuits, then you just link up with week 1 and week 2. Imagine that this is a resistor. Of course, it's not, but the methodology that you use, right, will be similar because the relationship between voltage and current is now similar to Ohm's law, right? Based on the concepts of impedance. So you solve these circuits for whatever variable that you want, and you will be in Laplace domain. Your solution will be in Laplace domain. There's only one more step. You need to take partial fractions last week, expressed as a linear combinations of the signals that you can get in the table, so as to get inverse Laplace transformations to get the signals in time domain. So this is the idea. And what are the methods? Any method, right? Any method. Sometimes you can just use Ohm's law. No need even to specify any methods. For example, over here, this is this is IS, and this is 4IS. Inflow equal to outflow, so therefore this current is 5IS. All right, add up. I plus 4I give you 5I. So I'm just putting this as 5IS by Kirchhoff current law. Inflow add up to be outflow. Then I use Ohm's law, something similar to Ohm's law. V is equal to the current times the impedance, right? V is equal to the current times impedance. Impedance is 1 over S, current is 5IS. Then I can get my V0 in terms of I. Okay, next then you check I. Where is I? I is here. So I can write down I by using similarly Ohm's law or impedance law. Now this is 0 volt. Right, and this is increased by 15, so here you have 15. Okay, over here this is 0. This is plus V0, so this is a node voltage V0S. Right, 0 volts plus another V0 give you this node voltage V0. 0 add 15 give you 15 over here. Then 15 minus V0 is the voltage across the 2 ohm resistor. Voltage difference divided by resistance give you the current flow. Okay, after that I can just substitute this into here. Then I get everything in terms of V0. Once you get everything in terms of V0, you just do algebraic manipulation to get V0, right? Group all those with V0 together on one side. Then those not related to V0, put it on the other side. There's only one term, right? 5 times 15 divided by 2. 5 times 15, actually 2 is bring to the other side of the equation, then you get 75. Okay, after that, we get these solutions, right, in Laplace domain. So you can see that everything is the same, right? Imagine this is a resistor, and then solve it similarly. Then you get a solution. The only difference is that you have to do one more step, take inverse Laplace transformations to get back your solution in the time domain. So to do that, right, need not remember anything, just refer to the tables. 1 over s plus 2.5. 1 over s plus 2.5, a equal to 2.5, e to the power of negative 2.5t is your solutions. Linearity property multiplied by 37.5. Right? And don't forget to put t greater than 0 or multiply by ut, because Laplace domain is only valid for t greater than 0. Any questions? Now, what about with non-zero initial conditions? You have seen the case of zero initial conditions, but in circuits, you know that your capacitor could be initially charged. When you want to charge up your handphone, you may not start from 0, right? You may start from 20%, so there's an initial storage, which you need to consider in your modeling. Okay, actually, in this case, right, you just retain this additional term, right? Do not set it to 0. So this is what we have. And notice that the left-hand side is current, all right? If this is current, then this is also must be current, right? This current is equal to this current plus this current, right? Plus this current. This basically means that you can represent this as this circuit model. Okay, let's start from I0. Right? I0 is this current, the whole thing, right? The whole thing. And this current actually should be flow in this direction. Why? Because if you write down this equation this way, IS, right, plus CV0, Kirchhoff current law, inflow is equal to outflow, which is your I1. So I'm saying that this inflow plus I0 is equal to my outflow I1, right? So this direction should be flowing towards the node. Inflow equal to outflow. So this one is represented by a current source over here, right? Because it's constant. Okay, the other one is actually what you have seen with zero initial conditions, 1 over SC. Right? 1 over SC, because if you look at I1 from here, I1, the voltage across it is equal to Vs, right? V divided by R, V divided by here impedance, 1 over SC, is equal to current. And you do just manipulations, bring this to the front, you get SCVS, okay, which is exactly this term. Right, so I1 is actually equal to SCVS because here you have parallel combination. Okay, which means that when you have current, right, you add up the current, so you have parallel combinations according to Kirchhoff current law. And this is basically the model of your capacitor in Laplace domain with non-zero initial conditions. So the only difference is that in addition to the one with initial conditions, you add a current source, right? CV0. Okay, if you want to express it in series, right, then what you need to do is just to rearrange this equation. Here you express current in terms of voltage. Here you express voltage in terms of current, right? So you just manipulate these equations to express voltage in terms of current. Now the left-hand side is now voltage. So your right-hand side, the two components should be voltage. Right? Voltage 1 plus voltage 0. This basically means it's series. Now the first one is still the same. Notice that is still 1 over SC, right? The second one represents this initial conditions, V0 divided by S. So V0 divided by S plus V1. V1, this is just impedance law, I times R, right? IR, IZ. Z is 1 over SC. This current multiplied by this will give you V1. Okay, actually this one is easier to remember. Right? Later on I will explain the way that you can remember this. Now if you want the other form, then you use source transformation, because remember source transformation can transform from this form into this form or the other way around. That means that parallel combination can be transformed into series combination can also be transformed into parallel combination. Okay, when do you use this form is depending on your original circuits, right? When your original circuits, if it's easier to handle in parallel combination, then you should use this. If not, then you should put into this form. But in any case, you can easily use source transformations to transform them. All right, so similarly for now I explained to you, right, how do we remember this model. Okay, one way is that you write down these equations to try to express into this form. The other way, of course, is just memorize by heart, right? Memorize by heart, only one. You only need to remember one, because the other one you can use source transformation to get it. So just remember one of them. Okay, I'll suggest that you remember this one for capacitor, right? And this is how you can remember it. Firstly, zero initial condition. Just now I said you must remember this, right? No other way. So write this down, 1 over SC. Okay, which means that I have the circuits, capacitors with a capacitors with initial voltage. First, I write down 1 over SC. Okay, next, notice that V0 is a constant. Initial voltage is constant. For example, your handphones, 20% constant, right? Unless you connect, you use it. So you remain constant. This is a constant voltage. Initial voltage is a constant voltage. Constant in time domain is equal to 1 over S, right? And the constant of 1 in time domain is equal to 1 over S in Laplace domain. So constants of V0 in time domain is V0 divided by S in Laplace domain. It means K is transformed into K over S. This basically means that, right, then you can just add this in, because it's easy to remember. Constant, time domain, Laplace domain become V0 divided by S, check table. Then you just add this in, right? Add this in, V0 divided by S. Now, in fact, this circuit model, okay, remember that I told you that if you have a signal divided by S, you are doing integration. So this signals pass through the capacitor and is integrating the current divided by I and add up with the initial voltage. Then you'll get the final voltage, right? So you have initial voltage. When current start to flow in, you have additional voltage. Charge out because of the flow of current. And then you get a final voltage on top of the initial voltage. Right? Yeah, if you want the other form, then just use source transformation. Right? How do you use source transformation? Just Ohm's law. This is voltage, correct? You want current. So current is equal to V divided by impedance, correct? V divided by impedance. Now V is V0 divided by S. Your Z is 1 over SC. Right, so this cancel out and C bring to the numerator, you get CV0. So this is just source transformation. So I'll say that this is easier to remember because constant become this according to property, right? According to the Laplace transformation table, and we put this in. Now similarly for inductor with zero initial conditions, with non-zero initial conditions, right? You have two expressions. Okay, one is that V square L dI dt, you get V is equal to L I S multiplied by S minus the initial conditions. Therefore, left-hand side voltage, right-hand side must be two voltages add up together. Okay, which means that one of them is this represented by the source. This is my V0. The other one is actually SL, right? Same as the one with the zero initial condition. Okay, if you want current, right, to be the subject, express IS in terms of VS, then you're adding up the current. This means parallel combination. Now for capacitor it's easier, for inductor it's easier to remember this as well. Okay, meaning that you write down SL, and then this is a constant current, right? Constant current in time domain. Constant divided by S in Laplace domain is a constant in time domain. Okay, which means that you can remember it this way. First, you write down SL. Then you remember that initial current constant in time domain. The table, right, according to the tables, for Laplace domain is I0 divided by S. So I add in this current source, I0 divided by S. If you want the other form, use source transformation. V is equal to IRO. So you multiply these two together. This is I times Z, right? You get this one. Because this will cancel out. You get Li0. So I'll say that for inductor, right, this is easier to remember. And you need the other form, you just use source transformation. Okay, in your second order differential equation, remember this formula. Alpha is equal to R over 2L for series RLC, right? Omega 0 is equal to square root 1 over LC. This one will be the same regardless whether is it series or parallel. Right? That's what we have seen in the previous tutorial. Now, if you've forgotten this one, right? Actually, you can do a quick check by using what I show in this slide. So basically, this is the idea. For capacitor, right, transform it into Laplace domain, 1 over SC, initial voltage, D0 divided by S. For inductors, right, for inductors, similarly, you have SL, right? If here you have two choices, right? If you want parallel combinations, maybe if you decided to use parallel combinations, then what will happen is that you have this something like this. Then you can see that you have one additional loop here, right? Which then will be more complicated to analyze. So since everything is series, then I should adopt series. So what you can do is that you get this one first, use source transformation to transform to this one, right? So even if you put parallel, eventually you should use source transformations to put into series so that everything is series, then you have only one loop. Then you take Kirchhoff voltage law around this loop. Resistor IR, inductor ISL, capacitor I 1 over SC. Right, then there are some voltages, voltage source, add them up, back to 0. Then you do algebraic manipulations, you can find the current. Right? So the current is equal to this form. Now what I want to show here is this characteristic equation. Okay, which means that, right, remember 2 alpha is R over L. So it's reflected here. And then omega 0 square is 1 over LC. Okay, which is also reflected here. Okay, which means that even if I forgot this one, right, I'll just do 1 or 2 steps using this. In fact, you don't even need to care about the initial condition. Right, you just get this one, then you get these characteristic equations, and then you remind you that this is my 2 alpha, this is my 1 over LC. So in the case that you forgot this, right, in the case that you forgot this, then just do this. And then, right, you will be able to get the formula, right? So I call retrieve the formula. Any questions? Okay, if not, let's look at the problem 2. Problem 2, right, you can see at the end of this question that the initial condition is not 0 now. You have a capacitor initially charged with 2 volts, right, and there's an initial current of 1 ampere for the inductor. So there are 2 energy storage elements here. And notice that your source, right, is not a DC. So therefore, here we can't use what you have learned in the time domain analysis to analyze it because this is not DC. But Laplace domain, no problem. Right, we can still transform it into Laplace domain. Okay, e to the power of negative t ut. I remember I said ut is just equal to 1 for t greater than 0. All right, so you are actually multiplying by 1. Right, it just says that this source is only valid for t greater than 0. And it's e to the power of negative t. That means a is equal to 1. Check the table, 1 over s plus a equal to 1, so 1 over s plus 1. Right? And this is my source, which then will be transformed into Laplace domain as 1 over s plus 1. Okay, what about the energy storage element? There are 2 of them. Let's look at the capacitor first. Capacitor is 1 over SC, C is equal to 1, so 1 over S. Right? 1 over S. So right now, 1 over S first. Okay, then remember initial voltage 2 volts. Check the tables. Constant 2. Laplace domain 2 over S. Right? So add this 2 over S. Now this one you can put in either side. Right? It doesn't matter. This series. So just put in either side. And then we have the model of the capacitor in Laplace domain. The inductor. Inductor is easier to remember the parallel combinations. First, write down SL. L is equal to 1, so basically you have S. Then initial current of 1. Okay, initial currents of 1, then initial currents of 1 in Laplace domain. Some sounds recognition. Okay, initial currents of 1 in Laplace domain will become 1 over S. The initial currents of 1 in time domain will become 1 over S in Laplace domain. So therefore, we write down this circuit model over here. Do I turn this off?
Prof, there's the stop subtitles.
Okay, never mind, I just exit. Thanks. All right, so here I'm explaining to you how do you remember the circuits model in an easier way, right? You have to remember this 1 over SC, SL, and initial voltage become initial voltage divided by S, initial current become initial current divided by S, right? 1 divided by S. And this one will be series, this one will be parallel. Okay, but of course, when you put them into the circuits models, then you have to decide whether which combination is better. Now here it happens that series is okay for this one. Parallel is also good for this one because here you have a parallel, right? Resistor, so it's good. Now even if you ended up with another configuration, just quickly use source transformations to transform it into a form which you want. Okay, so you only need to do this too. And then the other form, use source transformation, right? Of course, you have to know how to use source transformations. Okay, here we will then analyze these circuits to find V0. I read your question again, is to find V0. Now imagine that you have all this as resistor. Right, week 1 and week 2, you can analyze it by using any methods that you have learned. Okay, for example, if you would like to use nodal analysis, this is node voltage, correct? You want to find voltage, so naturally maybe you want to consider nodal analysis. Then you start assigning node voltages everywhere at the node. Now this is 0 is known, right? There's a node here which are 0. And over here, this voltage is unknown. You call V1. Anything that you do not know, you call name. This is already assigned V0. Leave it. Okay, here there's a node, right? Be careful. Here there's a node because there are two components. Join them together. This is a common node. This is also a common node. Now this node is okay because this is known voltage. Okay, this is V1. If this is V1, then there's a drop in voltage. So this V1 minus 2 divided by S. Right? Okay, which means that now you can apply KCL at node V1, node V0, write down two equations with two unknowns, solve for V0. No need to solve for V1, right? No need to waste time. Solve for V0, and then you get your solution. So this one way. Okay, the method is not fixed, right? Because it's not specified. So it's up to you to do, right? Up to you to choose. But if you do not want to solve two equations, right? Or you're not comfortable with solving two equations, then transform the circuits using source transformations. Okay, here I will transform this into this. The Ohm's law, current multiplied by resistance give you voltage, right? Give you voltage source in series with 1 ohm. Okay, this circuit is now easier to analyze. There's only one unknown. There's only one unknown. Okay, this source actually you can swap it over here and then combine them, right? If you want. Okay, if not, you can also analyze it directly. Okay, then you can write down these equations. Firstly, you combine these two, actually you get this one. All right, this increase, this decrease. So increase minus this, and then minus V0. V0 is here. And divided by the total impedance. 1 plus 1 over S. Or imagine you have two resistors, R1, R2, add them. R1 plus R2, the Z1 plus Z2. Okay, right hand side is easier. V0 divided by 1. Current through the 1 ohm resistors, right? I'm using Kirchhoff current law now. Inflow is equal to outflow. V0 divided by S, current through the inductor. This is a constant current source, write it down, 1 over S. So this is one equation with one unknown, all right? V0 only. Therefore, you need not solve two equations, right? If you just use source transformations to simplify it further. Okay, or you solve directly, right? The original circuits with V1 and V0 is also fine, right? So method is not fixed. Now, if you have problem with this expression, right, even after you switch it to this position, I suggest you do it this way. You assign a current called IS, right? So this is IS. Then you take Kirchhoff voltage law around this loop, all right? Take Kirchhoff voltage law around this loop. What will happen is that you, from here to here, you get 1 over S plus 1, all right? No problem. Okay, then over here, this is passive component, right? High to low, this low to high, high to low drop. IS times 1 ohms, all right? Ohm's law. IS times 1 ohm. Here there's a drop again, minus 2 over S. All right, drop. And here, passive component, remember, right? Always energy must flow from high to low. Otherwise, it's a source, right? Otherwise, there's a source, there's energy there to push up against the law of nature. Right? We naturally, it should be from high to low. And then I have I, Z, 1 over S. Okay, then here, now V0 is your node voltage, right? So remain it because you want everything expressed in terms of the node voltage. So when you come to here, there's a drop, right? Drop. So you put minus V0. Then you go back to 0, right? You go back to 0. Now group all the I together, or IS, this is actually IS. Okay, and then bring the remaining terms to the other side of the equation, you actually get this one. Right? So many ways actually. Shift this around, easiest way, you can get this one. Or you just go one route, write down the equations in terms of a V0. Then you solve for IS, then you know what this current, right? This current is IS. Inflow is equal to outflow. Right? Inflow, IS, is equal to outflow. Okay, of course, the concept is similar to week 1 and week 2, but however, right, the equations now is not scalar. You can't combine some of the terms. This is the first time, so I will show you in details. Now, in actual facts, you need to work out step by step. Right, I will show you step by step, but only for the first couple of tutorials. You need to work it out, right? As I stressed to you right from the beginning, the key idea is that you must be able to do all your tutorials without reading your solution. Okay, if not, then there's something which is not there yet. You need to push harder. So that's the gauge. Because by reading, right, by reading, things will become easier if I provide you the details. Now, if the details are not provided, it means that, right, you are expected to work it out. For example, the example in the note, try to work it out on your own. Okay, here you cannot press calculator anymore. Unlike the resistor network, you cannot press calculators. You must do it step by step, right? So therefore, the foundation is very important. Okay, I'll show you step by step how do we solve this. Okay, we want to get V0. Right? So if these are constant, then no problem. But unfortunately, these are not constant. So do it one by one. First, I'll put this into V0 because divided by 1. Right, this is straightforward. The rest, no change on the right-hand side. On the left-hand side, 1 plus 1 over S. I just put them into S plus 1 divided by S. So this is basically this term. Right? After that, I bring S to the numerator. Right? Bring S to the numerators. And then this is how it appears. Okay, this divided by S. So S divided by S become 2. No more. Right? No more S term. So this is on the right hand side. I also group these two together. Take out V0. And I have 1 plus 1 over S, which is S plus 1 divided by S. S plus 1 divided by S. So this is what I have. After that, I want to get rid of this denominator. So I multiply by S plus 1. Right? When you multiply by S plus 1, on the left hand side, you must also multiply on the right hand side. So on the left hand side, this term will disappear. On the right hand side, right, you will square this. And this one you will multiply by S plus 1. Therefore, you get the next equation. I'll reproduce these equations over here. Now here I can now group V0 together. All right? I can now group V0 together by simply moving this to this side. And then I'll move those terms not depending on V0 to the other side. And then I get the next equations. Okay, after that I divide by this term. Divide by these terms. And then simplifying it, I get V0.
Sorry, Prof. Can you go back one slide?
Yeah. What's the question?
I'll just need to take a photo, take a look.
Okay. So look at these solutions, right? Remember last week tutorial? Expand it out by partial fractions, and then take inverse Laplace transformations based on the table, right? Based on the table, expressed as linear combinations of the known signals. So the next step is that I would normalize this, right? 2s squared to 1s squared. Okay? So that I have the s squared plus s plus 0.5. Now when you divide the denominator by 2, the numerator should be divided by 2 as well. Okay, first thing that you need to do is to check whether you can factorize this or not. Sometimes you can factorize, right, into real factors, I mean. Okay, if you end up with a complex solution, it means that you can't factor it into real factor, right? Then you just leave it. Okay, which means that I can only express it as a linear combination of two fractions. One is first order, the other one is second order. Now first order, right, the numerator is one order less, so it's constant. Now this s squared, one order less, s1, right? And then plus a constant. So the numerator is always one order less. Right? Then how many coefficients? Naturally, it depends on the order. All right. If you have one first order, only one term, one unknown. Second order, one less, right? S1, so you have two unknowns. So this is a key idea. Now you have three unknowns: A, B, and C. Okay, I will reproduce it over here. Now the key idea here is that you want to find ABC based on this equation. Left-hand side must always be equal to right-hand side for any S. Okay, as I mentioned to you last week, if you just substitute three values of S, three different values of S, you get three equations, right? For example, you put S equal to 0, you get one equation. You put S equal to 1, you get another equation. You put S equal to 2, you get another equation. So long as you are not divided by 0. You cannot substitute a value which will end up divided by 0, that means not defined. Then you get three equations. Three equations you can solve for three unknowns. If you have a powerful calculator, you just key in these three equations, you can try. You'll get the same values of S. So go back and try, substitute three values of S, get three equations, solve the three linear equations with three unknowns. You can get ABC. Okay, but there's also another easier way to solve it. Right, later on I'll show it to you. Okay, before that, just to take note this one first, s squared plus s plus 0.5 can be put into this form. This is how it works. S squared plus s plus 0.5. Okay, I take half of this, right, this one, half of this, and then square it. Okay, if I add this, I must minus this. Okay, then it is still this equation, correct? It's still the same. Okay, why I add this is because it can be put into this form. S plus half squared. Right? S plus half squared. 0.5 minus 0.5 squared is 0.25. 0.25 is 0.5 squared. Okay, and in other words, it can be put into this form. This form you can find in your Laplace transformation table. Okay, you cannot find something like this, but you can find something like this, right? So this is the purpose. You want to put into a form which you can find in the table. So just take note, this can be put into this form first. Right, before that, we must find A, B, and C. Now, firstly, let us find A. If you multiply both sides of the equation by s plus 1, right, then this one will cancel out, then this will multiply by s plus 1, and you put s equal to -1. Remember, I said you can put any value, but if you put directly, then what happens is that you're dividing by 0, and the rest of the terms, right, will still be around, right, even if it's not dividing by 0. Now I multiply by s plus 1, and you put s equal to -1, then this becomes 0. Then you only end up with a, right? So here you just put s equal to -1 without this term. So this is called cover-up rules, and it's equal to 1. Okay, therefore I can solve for a without having to solve 3 equations with 3 unknowns. So this is the idea. Okay, after you get a equal to 1, then only left with 2 unknowns. And these 2 unknowns also can be solved easily if you choose your s wisely. If I choose s equal to 0, then b disappears. No more b, there's only c. Right? Instead, I can solve for c directly. Now put s equal to 0 also make things easier. Right? This will become 0.5 only, this will become 1 only, and the rest of the term you can see that, right, I can just simplify it very, very easily by putting s equal to 0. Then s is equal to -1, okay, which means that this is known. Now if this is known, there's only one unknown. Just put any value of s into this expression, you can get b easily. Right? For example, put s equal to 1, you want to try s equal to 2, s equal to 100 is also fine, right? But choose a term which is easier to calculate. 1 is good. And you get b equal to -2. Okay, which means that I can now expand my solutions that I found through algebraic manipulations in Laplace domain into 2 linear combinations, right, of these 2 fractions. Okay, next is that I can't find anything like that in my Laplace transformation table, but I can find something similar, right, because I can put this into this form. Now compare this with this expression, or rather compare the denominators. You can see that a is equal to 0.5, omega is actually equal to 0.5 as well. Okay, but the numerator you must match carefully, right? The numerator is actually 2s plus 1. But here you want s plus a, right? That means s plus 0.5, a is 0.5. Okay, but it is fine because what you can do is that you take out 2, then you have s plus 0.5. Okay, and this is your a as well. So this is my a, this is my omega, which means that, right, it's e to the power of -0.5 t or half t cosine 0.5 t or half t. Now don't forget this too. This linearity property, right? Linear combinations. So constant multiplied by this, okay, which means that I'll get this 2 because of this constant. And this one is from Laplace transformation table. Okay, as for this term, it's just 1 multiplied by e to the power of -1t. And don't forget to put t greater than 0 or multiply by ut. Ut means equal to 1 for t greater than 0, right? Multiply by 1 for t greater than 0. Any questions? Okay, so I hope everybody get the idea. Given the circuits, put into Laplace domain models your energy storage elements, right? And then the relationship between voltage and current is similar to Ohm's law now. It's called impedance law. Then treat it as if they are resistors. Solve for it. In the end, you get some solutions in terms of S. Then you must take inverse Laplace transformations. Okay, if you can take directly, go ahead. If not, express it as linear combinations of those signals that can be found in the table. Right? For example, I can find these 2 tables. I put them as a linear combination of these 2 tables. This is the original one. I put them as the linear combinations of the 2 signals. Then I take inverse Laplace transformations by making use of the linearity property. Okay, in fact, at this stage, right, after going through Laplace transformation, you may want to review your notes for the differential equation time domain analysis as well. Okay, and this is how it works. For example, right, second order. A real distinct means you can factorize it into two factors, right? If you have this one, if you can factorize into two factors, then that's nice, real factors. Then you get these two real factors, partial fractions, and then you take inverse Laplace transformation, you get the solution, all right? And this is over there. Okay, therefore, I will say that you can find this in the table, even if you have forgotten it. Okay? You want to review this question 5.2 as well, right? It's related to this concept. Okay, as for under them, right? Just now I showed you one case. Under them, what you need to do is to put it into this form: s plus alpha square plus beta square. Okay, then you look at the Laplace transformation table. You have a linear combinations of the these terms, e to the power of negative alpha t cosine beta t, right? Linear combinations of them, and then you can get the solution as well. So in other words, right, if you forgot the three forms of solutions, check your table, it's always available. Under them is the last two. Or just circular this one. A1, e to the power of negative alpha t sine omega t, plus A2, right, e to the power of negative alpha t sine omega t. This omega d, you must calculate. Okay, as for over them is just two of this, right? Because you have two alpha, alpha 1, alpha 2, linear combination of these two. Okay, the only one is the critically damped, right? Critically damped is a combination of these two, right? These two, because there's a repeated root. Now, some of you will be wondering why there's this additional, this t, actually because it's repeated s squared. Right? For example, if you look at this one, actually this is one way to calculate the coefficient, but as far as second order system is concerned, as in this case, it's quite easy to calculate. I'll just show you one example. If after you solve your circuits, you get this solution, right? Remember, Laplace transformation is that you transform the Laplace domain, you solve the circuits in Laplace domain, then you get the solution. The only difference is that you have to take inverse Laplace transformations to get back the signals in time domain. If you get this one, then try to factorize s squared plus 10s plus 25. When you factorize it, you realize that it's not two distinct factors. It's a repeated one. S plus 5 bracket squared. All right? S plus 5 bracket squared. Now, this term cannot be found in your table. There's no such term. If you can find it, then just directly take. So if you cannot find, actually there's one easy way, right? S plus 10 is s plus 5 plus 5. Why I get this 5? Because here s plus 5. Then you divide it by s plus 5 squared. All right? It means that I expand this term into s plus 5 plus 5, s plus 10. And then divided by s plus 5 squared. Now here you can see that this basically cancel, become first order. All right, so your A1 is actually 1. Okay, your A2 is actually 5. This means that actually this is what's happening because there's this repeated terms, right? And you cannot find this term in your tables. So you express them as a linear combinations of two terms, which can be found in your table, right? Which is this term and this term. Then when you take inverse Laplace transformations, you'll be able to get, right, two terms. The only thing is that one will have the factors of t, okay, over here. So this is actually the case of the critically damped. Any questions? Okay, if not, let us move on to question 6.4 first. Right, I will jump the sequence a little bit because question 3 will require the concept of dot convention, right, which I'll explain later on. Now, here, right, you need to obtain the transfer functions. Now, basically, transfer function is just the relationship between output and input. So you have input voltage, you have output voltage. The ratio of output over input is called transfer function. Now, for transfer functions, even if it's not stated as in this question, you can always, right, assume zero initial condition. Right? Always zero initial conditions, okay, which means that when you transform your circuits models, this will be just 1 over SC, this will be just SL, right? No need to consider the initial condition. Now, transfer function, as I said, tells you the relationship between input and output. In circuit analysis, your input could be either voltage or current. Right? Similarly, your output could be either voltage or current. And hence, actually, your transfer function may have various combinations. Now, firstly, why do we use transfer function? You use transfer function when your input will change quite frequently. Right? For example, if I give you a question, says that part 1, obtain the output for a DC input Vs equal to 5 volt. And also obtain the output for Vs equal to a exponential term. Then obtain another one for Vs equal to a AC signal. Right? Maybe find sine omega t. Now, one way is to solve this circuit 3 times, right? One way is to solve this circuit 3 times. The other way is to get the model, so that after that you only need to substitute the input into this model to produce the output. Then from here you take inverse Laplace transformations to get yt. So this simplified your calculations significantly, in the sense that you need not repeat it for 3 times. You only find your models. If this model multiplied by your input, if your output, take inverse Laplace transformation, right? So these are key ideas. Okay, firstly, we have to find the transfer functions. And in order to do that, you must first transform your circuit into Laplace domain. IT become IS. 1 over C become 1 over SC, C equal to 0.5. 1 over 0.5 is 2, right? And then 2IT become 2IS, V0 become V0S, 3 ohms remain, 1H become SL, L equal to 1S. After that, treat these circuits, right, as if it's a resistor network, and then try to solve for it. Okay, actually, it's quite similar to the previous questions that we have solved. This inflow, IS, 2IS, inflow equal to outflow, so this is 3IS, right? I plus 2I give you 3I. Okay, so this is left hand side. 2I plus 2 plus I, right? 2I plus I. Right hand side will be equal to V1 divided by this series. Series, you add them up, S plus 3. Okay, and that means that I'm applying Kirchhoff current law at this node. Inflow equal to outflow. I plus I is equal to 3I. Right, next, notice that IS is here. Right, IS is here. IS is actually Vs minus V1, voltage across the capacitors, right? Vs minus V1 divided by the impedance. Impedance is 2 over S. So you get a current, Is. Okay, then you substitute this into here. You get an equation with only in V1 and Vs, right? Only V1 and Vs. That means that from here I know how V1 is related to my Vs. So after that, do some algebraic manipulations to group V1 together, right? Group V1 together, Before that, you may want to simplify it step by step. Right here, basically what I do is that I just bring S to the numerators, and then I separate these two terms clearly. Okay, after that, I can bring this term to the other side of the equations to group V1 together. Okay, then I get V1 in terms of Vs, right? Okay, if you want express V1 in terms of Vs directly, and this is how this voltage, this node voltage, can be obtained in terms of Vs. But read your question carefully. What we want is not this node voltage, but V0. Right? V0 is output. Well, once you know V1, you can relate to V0 by voltage division law. V0, voltage across the 3 ohm resistors, is a portion of V1. This is your V1. Right? According to the ratio of the impedance. Right? 3 divided by S plus 3. Okay, even if you forgot your voltage division law, as I said, just use Ohm's law. Find this current. What is this current? V1 divided by series. Right? S plus 3. So V1 divided by S plus 3 is actually the current flowing through here. And according to Ohm's law, this current multiplied by 3, current multiplied by 3 is V0. Right? So this form basically the voltage division law. But you can see that voltage division law is faster. You just write it down directly. Otherwise, you have to break it into 2 steps, right? But you get the same thing. Okay, after that, I can then substitute this whole thing, which is V1, into here. Then I'll get the next expression. Some of this term can be cancelled out after you multiply them together. And this gives us this term. Now, this term is nice because remember, right, if your input is changing, so it's 5 volt in Laplace domain is what? 5 divided by S. Alright? Then you go here, put 5 divided by S into here. After that, expand it out by partial fractions, take inverse Laplace transformation, you get V0S. See, in the sense, for any value of Vs, you just substitute here and start from here. You need not start from the beginning as what we have done just now. Right? It's a long step towards obtaining this. But once you get this model, or any input, multiply by the transfer function, will give you the output, because transfer function is the ratios of output over input. Right? Therefore, you multiply by input, you get the output. So this is the ideas. Now for any input, just put it here, calculate Vs, take inverse Laplace transformations. I can get my VOT, right? So this saves a lot of steps. Now to summarize, right, transfer function is a concept that used to model a circuits with variable inputs especially. So that once the input change, we need not analyze the circuits again. We use the transfer functions to predict the output, and then we take inverse Laplace transformation. Any questions?
Sorry, it was really fast. Can you go back a few slides? Like 1, 2, yeah.
This one?
Yep. Sorry.
No problem. So, please take note that go back and try to work it out on your own until you reach a stage that you need not refer to this anymore, right? So this is just in case you cannot remember, you refer, but the gauge is that you must be able to do this without referring to it eventually. Right? Okay, the last problem, right, involving something we call dot convention. First, let us understand why do we need such convention, such standardization? Right? Is it because when you wire wires around ferromagnetic materials, right, this is used in a transformer. All right. Here you have ferromagnetic material. You want to step up or step down the voltage, and this is also called magnetic couplet circuits. They are not directly connected together. You can see, right, this wire is not connected to this wire, but they are coupled through the magnetic flux over here. So the circuit symbol is something like that. There's no connections, but there's a coupling between them. Now there's one problem, right? The directions of your induced voltage actually will depend on how you wind this, because according to right-hand rules, right, the flux directions, if you curl your finger in this form, representing the directions of the wires, okay, then the flux is actually the directions of your thumbs. Okay, but this wire can be either this way or the other way around, and you will produce different directions of the flux. Okay, imagine you receive this circuit, a transformer, as an engineer. How do you know what was produced in the factory, right? Because everything will be sealed up. Even if it's not sealed, it's very hard to predict the directions of the winding. So this indicates that, right, we need something to indicate the polarity of the induced voltage. Okay, because it all depends on the way the coils are manufactured in the factory. And this basically, right, comes with the dot convention, which is basically to help us, right, to determine the polarity of the induced voltage, right, the mutual voltage. So it's something that is standardized, called dot convention. It is something actually very simple, only this sentence. If a current enters the dot terminal of one coil, there are two coils, remember? Two coils, right? So if you want to determine the induced voltage of the other coil, you look at, if you want to introduce the induced voltage of one coil, you look at the current and the dot of the other coil. Right, let me put it this way, right, by one example, and then we follow this through. If a current enters the dot, let's say I1, enter the dot, all right, then this indicates the polarity of the mutual voltage at the other coil, which is this coil. It says that the polarity of the mutual voltage in the second coil, this coil, is positive at the dotted terminal. So this dot is at both sides, and he says that this enter the dot, right, then it's positive at this coil, at the other coil. So enter dot, positive, right, at the dot. So the dot is used this way. At this coil, you look at entering. At the other coil, right, you look at the polarity. So similarly, if you have current on the other side, then I2 enter dot, then the voltage induced by I2 will be positive at the other side, right? So it's always the other side. And altogether, there are only three cases, right? What if you apply the current the other way around? All right, you apply the current the other way around, then you are leaving the dot. By leaving the dot, it means that you go through the coil first, then the dot, right? This one you go to the dot first, then the end of the other coil, right? This one you go to one end first, then you leave the coil at the dot, and this is called leaving. Now this one say enter, positive, so leaving, negative. Right? As simple as that. Enter dot, positive at dot, leaving dot, negative at dot. Okay, there's only one more possibility. Okay, actually this also reflected here. It means that if you enter this dot, but this dot is not here, but over here, right? Then this just means that it's positive at this dot. So it's positive voltage here at this dot. Right? This is because of the winding, okay, which was actually fixed in the factory. So we get the circuits, then we know, right, how this was actually designed previously, and this basically let us analyze the circuits, okay, by using this convention.
So remember, enter dot positive, finish, right? The rest you can deduce it easily, leaving dot negative. And also notice that this mutual voltage, right, is induced by the current of the other coil, right, of the other coil. Okay, let us look at this circuit. Now this circuit is actually the same example in your lecture notes. I think it's example 5 if I'm not wrong. So actually you already have the solution, right? But here, let us just go through it. Okay, firstly, this is a switching circuit. Originally at A, switch to B when T is equal to 0. And here you have a DC source, right? DC source. And he says that hold at A for a very long time. When you say very long time, it means that you give sufficient time for it to reach steady state, right? Before you switch to B, and then you want to find this current for T greater than 0. Okay, let us consider the case before switching, right? So given this circuit, and it's DC, and at steady state before switching, inductor will behave like short circuits, right? At steady state. So remember that energy storage element at steady state, it's as if they are not there because they have a certain property. V is equal to L di dt, I constant, D equal to 0. So look at this circuit, it's just resistor, correct? Just resistor, which means that you can solve it easily by using Ohm's law. Okay, here, for example, the current flowing through here is 60 volt divided by series 12. So 60 divided by 12, 5 ampere. Okay, the other one, no source. If no source, there's no current. Right? Current equal to 0. That means voltage equal to 0. 0 volt divided by any resistance is 0 ampere. Now, we also know that L di dt means current cannot change suddenly. So therefore, immediately after switching, your current I1 has to start at 5. Your current I2 has to start from 0, right? So this is a key idea for switching circuits. Okay, when we switch the positions of the switch from A to B, then you are disconnecting from your source as well as your 9 ohm resistor. And this is directly connected to ground. Therefore, this is your circuit now. Now, in writing down the equations of this circuit, you must consider the coupling, right? Coupling. Now imagine these two are far away in the air. There's no coupling between them, no ferromagnetic materials to connect them. Then they are just two independent circuits. Okay, but they are connected by ferromagnetic materials. So therefore, there's a coupling between them, right? And there's a mutual voltage between them. Okay, but what you need to do is to write down the equation first without the coupling. Okay, without the coupling, there's no problem. So imagine this is not there. Then you take KVL around this loop. This is what you can write down, right? This is voltage across the resistor, Ohm's law. Voltage across the inductor, L di dt, I1, L1. This one, no problem. The only thing is that you must consider the mutual inductance. But you write down this first. Then remember your dot convention. Right? It says that here, enter the dot. So it's positive at the dot. Right? Positive at the dot. And the mutual voltage is induced by I2. Right? I2, the I2 dt multiplied by M. Positive at the dot. So we add this in. Okay, next, same thing for coil 2. Imagine there's no mutual inductance. Write down the equations. 12 is 10 plus 2 series. Voltage across 10 plus 2 give you 12I2. L2 di2 dt. Alright? Then look at the first coil. Enter the coil. So positive at the dot on the other coil. Right? Enter coil, enter dot, positive at the dot, and it's M di1 dt, induced by I1. Right? So it's always induced by the other coil, right? Here is induced by I1, here is induced by I2, always the other way around. Okay, this means that your equation, you can see that you have I1, then you have the mutual voltage by the other coin. Right here, coil 2, you have I2, then you have the mutual voltage induced by the other coin. All right? But because of that, you also make this circuit harder to analyze in time domain, because the left-hand side equations, you have I1 and I2. Right-hand side, you also have I1 and I2. We can't solve this, right, as a first-order equations that we have done before. So one way is to try to transform this circuit into another equivalent form. Now the key idea is that here you have a current I1, here you have a current I2. Okay, can you combine them into T junctions with a current with I1 plus I2? Right? Because this I1, this I2, can I put it into this T equivalent form to represent this? Okay, the idea is that yes, you can if you try to look at this equation in another way, right? Now, how do we get I1 and I2? You add I1 to the first equation, right? Because this is di2 dt, so you add m di1 dt. What you have is that you will get this term, m d I1 plus I2. Now, when you add this term, you must minus this term, all right? Minus this term. So these terms will end up grouped together with here because these are all di1 dt. Okay, then I get some current, right, which is I1 plus I2. Okay, similarly on coil 2, right, on coil 2, I will add di2 dt because here I have I1. So I get add I2, then I'll get I1 plus I2. Okay, when I add this, I must also subtract this. This means that I will then put this together as one term, and this one I will put it together with this as di2 dt. Okay, in other words, the original equation, right, without this term in the red is put into the second equations by just adding something and subtracting something. And the key idea is that I now get this common term among them. Okay, remember the common term means share, right? Share voltage. Okay, in fact, when you take Kirchhoff voltage law around two meshes, the mesh analysis, remember, mesh current I1, mesh current I2, right? I'm following the same directions. Then actually you can write down this equation. This is voltage across 3 ohm resistors. This is voltage across the inductor, L1 minus M. Okay, here, when you come to here, this is I1 plus I2 now, right? Then the voltage will be M, I1 plus I2 dt, okay? Because this current is I1 plus I2. Okay, when you come to the other side, you have this shared branch. So naturally, you have this shared voltage, right? The only difference now is that here you have 12 I2 L2 minus M di2 dt plus this, okay, which means that you can put into this form, which is in a form more familiar with us, and we can solve these circuits, right, by using, for example, mesh analysis, because we're interested in solving the current. Now you can also use nodal analysis, of course, V, right? And then your I2, what you need to do is that after you get V divided by all this impedance, it will also give you the current. But here I'll use mesh analysis directly because we're interested in solving the current, I2. Read your question again. Okay, I suggest that you deal with numerical values rather than the general notation. My first thing is easier to deal with numerical values. Secondly is that some of the terms could be simplified once you put it into numerical value. In particular, L1 minus M. L1 minus M become 0. So actually there's zero inductance, right? That means no inductor there, nothing. So this is simplified to 0. And L2 minus M, 8 minus 2, 6. Right? Mutual inductance, 2. Just put 2. So this is easier to analyze now. And we can transform it into Laplace domain. Now, these are all inductor, right? Called inductors. So as I said, remember this circuits models. And then transform into the other form if necessary by source transformation. And this is easy to remember. Just write down SL, constant current, initial conditions, in Laplace domain I0 divided by S, right? Current at, so parallel, I1 plus I0, I have this circuit model. Okay, in other words, this 6H, right? 6H is equal to S multiplied by 6, L equals to 6, okay, with the initial condition. But this one, I2 is equal to 0. Right here you have I2 equal to 0, so it's just 6S. Now there's no inductance here, right? Nothing, but there's one more inductor here, 2H. Now 2H basically is 2S, no problem. Okay, but initial condition, be careful. The current through here is I1 plus I2. Therefore, initial condition is this plus this, right? Which is equal to 5 ampere. 5 ampere in Laplace domain is 5 divided by S. 5 divided by S. So which means that it can be put into this form. Now, if you put this over here, right? Let's imagine that you put this here with a current source. Then you created one more mesh, correct? One more mesh. So this is not advisable. Series is better. That's where you will use source transformation. Transform it into series. Right, how do we do that? Ohm's law, just Ohm's law. V is equal to IR. This is current, I. 5 divided by S is the current, right? Times Z, 2S. Then you get 10. Right? You get 10. So it's easier to remember this way. Put it into this form, use source transformations to transform it into this form, and then put it back into the S domain circuits. Right? So this is what we get. Now, as I said, if you want parallel, go ahead, but then you create one more mesh. Right? One more mesh to solve. So it depends on the method that you use. If you use mesh analysis, then it becomes one more mesh. But if you use nodal analysis, actually, right, it is also fine, because this does not create a different nodes. Right? It's still the same node. Because here we use mesh analysis, so therefore I'll transform it to this form, and now I'll proceed to solve this system for t greater than 0. Right? Remember, we are solving I2 only. So no need to waste time to solve for I1, just I2. Okay, here, after that, treat it as something similar to resistor network. Use any methods, right? Any methods that you wish. For example, nodal also can, mesh analysis also can, to solve these circuits. The only difference is that after solving it in Laplace domain, you have to take inverse Laplace transformations to get back to time domain. I'll use mesh analysis over here, which says that, right, you take Kirchhoff current law around each of the loop. So let's start with mesh 1. Right? Mesh 1 is on the left. Here you have 3I1S, right? This impedance now. So you have 2S multiplied by the current flowing here through this branch, right? Be careful, is I1 plus I2. I1 plus I2. So times I1 plus I2, and then here minus 10 back to 0. Then these equations can be further grouped together by grouping I1 together and then separate I2. Then you get one equation. But you have two unknowns, I1, I2, so you need one more equation from the other side, right? From the other side, and this is obtained by taking another Kirchhoff voltage law around this loop. So this is I2. Okay, if you take Kirchhoff voltage law around this loop, you can write down this equation. Voltage drop across 12 ohms, 10 plus 2. My voltage drop across 6S. Okay, voltage drop across 2S. Current is I1 plus I2, and this voltage is here. Now you can see that this is your shared branch. Right, this is actually your shared branch. Here we get two equations with two unknowns. Okay, then we solve these two equations with the two unknowns. Now here you can see that you can't press calculator anymore, right? So the basic is very important. Solve two equations with two unknowns. The easiest way is substitution method. Substitution method, first, what you want to solve? I2, right? You don't want I1. If you don't want I1, then you express I1 in terms of I2 from any of this equation. For example, if I get from equation 2, I express I1 in terms of I2, right? I1 in terms of I2, and this is what I get. Then I substitute into the other equation. By doing so, you only left with I2, because I1 is substituted by I2. I1 is substituted by I2. You only left with I2. Once you only left with I2, the rest are algebraic manipulation. Right? As I said, do it step by step. And no easy way to jump. Right? You will lead to careless mistake somewhere. Okay, here, I'll get rid of this denominator first by multiplying by 2s on both sides of the equation. So on the right hand side, I'll get 20s. And this 20s happen to be same as this multiplied by this, so they can be cancelled out. Right? They can be cancelled out. Okay, and after that, just group all the I2 together. And here you have I2. Alright, you can group them together. And 30 is the only term not depending on I2. You can bring it to the other side of the equation. Okay, then you get negative 30. Okay, the rest, put them together and simplify them if you can. This is what you get eventually, right? After simplifying this whole thing. For example, 4s squared minus 16s squared give you negative 12s squared. Okay, after that I can get I2. The only thing is that this is in Laplace domain, right? This is Laplace domain. Now here I will take out 12. Okay. And then 30 divided by 12 is this term. Okay, next, you would like to take inverse Laplace transformations of this. And this term you cannot find in the inverse Laplace transformation table, alright? But you should try to factorize it. Unfortunately, it can be factorized into s plus 1, s plus 3, real factors, which means that it can be expressed as a linear combinations of two first order fractions. Okay, this means that the remaining job is to find these two unknown, A, B, or K1, K2, or A1, A2, right? It's just a notation. And to find this, you use your carve-out rules, right? Carve-out rules, or basically you multiply by the factors, substitute that value into it. You can check that K1 is 1.25, K2 is negative 1.24, right? Or, as I said, even if you put two value of s into it, then you get two equations with two unknowns, you can also solve for it. For example, if you put s equal to 0, right? If you put s equal to 0, then you get something like this. 2.5 divided by 3, left hand side. Right hand side is K1 plus K2 divided by 3, one equation. So s equal to 1. s equal to 0. Right? Then you put s equal to 1, you get another equation. Then you solve these two equations for k1 and k2 also can, right? Because now this calculator can do this quite fast as well. So do whichever way you think is faster. Okay, but this is only when you can factorize into distinct. Right? Distinct. Okay, for those that cannot be factorized, okay, we need to do it very separately. Only can factorize into first order real factors, then you can calculate that quite easily. Okay, finally, we take inverse Laplace transformations. S 1 over s plus 1 is e to the power negative t, 1t, a is equal to 1. A equal to 3, e to the power negative 3t. Right, then we use linearity property, there are two terms. Okay, I hope everybody get the key ideas. By transforming your capacitors and inductors models into S domain model, right? That means SL, and 1 over SC, and also considering the initial conditions, we can analyze the circuits as if this is a resistor networks. Then we get the solutions, right, in Laplace domain. After that, we factorize it into linear combinations, right, of some fractions which can be found in the Laplace transformation table before we take the inverse Laplace transformations. And this can be obtained from the table, right, without having to do any calculation, because as I said, people have already calculated that, show that this is true, right? So we just use it. Any questions? Okay, if not, that's all for the tutorial. Thank you.
Thank you, Prof.
Thank you. Bye.